All righty. So, got your exam scores back. As I mentioned in the announcement / email, it just it seemed apparent that some of the calculation exercises were probably not done the way I really intended. I just graded them, and but we probably, on the final, I probably just won't do those types of calculation exercises. Now, a lot of the exercises on the exam were not that kind anyway, and actually that's one reason I made the first two problems worth quite a number of points. I mean, because usually any answer I go with 4 points and figure it all averages out quite nicely. But I thought in this particular case, I was kind of waffling. Well, did I want to count like problem number one worth 32 points out of, I think, 112? And was considering maybe making them 2 points apiece and all that. But actually, on the whole, people did really well on those, so it's kind of nice to give points that way. And then the other is they weren't the type of problem that you can just throw into something and get an answer out. So I ended up having those worth the 4 points for every answer. And the tests, the final won't look a lot different than what you're used to from the first couple of exams. But like I say, I probably won't have anything that says, determine the definite integral unless it's something really strange. Okay. So for instance, the derivative problem that was using the second fundamental theorem of calculus in whatever number that was, maybe 6, that generally speaking, you can't just go find the answer to that because it's all symbols, and most things can't quite, even though they're really good with symbols, they can't quite handle that. Okay, so we are in the last module, in the last chapter we'll look at, chapter 7. I've opened up some things on that. I've been able to, this morning was when I was able to do it, I was able to put just the beginnings of some videos on some exercises from 7.1 in there. I don't have the upload spots yet for the homework. And we will do one last project. It will be, I'm pretty sure, on, if you click on the project thing, it's got, if you read through it, the very last thing it says is the project will have something to do with comparing shapes, or like volumes and surface areas. Well, actually, no, it's not going to. It's going to be a build-up problem or modeling problem with the southern pine beetle. That's what it's going to. So it'll be a kind of a forestry recreation thing. Now the recreation part, because this will be in the project write-up when I write it. It's actually based on what I did for a master's thesis. So when I got my master's in operations research, I had a research assistantship that paid me to work on looking at the problem of helping to control the southern pine beetle infestations in southeastern forests. And so a nice forestry, biology, nature kind of problem. And part of that problem had to do with just kind of coming up with a model for the growth of the spots and all that. And it's nicely geometric, and so I think it'll make a nice application to fit Chapter 7 here. And it's also kind of a biology thing. I've been trying to do a lot of biology-oriented stuff. Any questions about anything right now? Yes?
Can we ask about the project?
Sure, you can ask about the project.
I was having a lot of trouble on 2.7 and 2.8.
Okay, what are 2.7 and 2.8?
Which is, it was the separation of variables for the...
Oh, yeah. Yeah, okay. So in the project, you have something like dm dt and m to the 3/4. There's an a here, I think, right? And then 1 minus little m over uppercase M to the 1/4, like that. Is that it?
Yeah.
That's it, yeah. Yeah, it was kind of interesting. And I don't really remember if I was just looking at this or if I was looking at multiplied through, so AM to the 3/4 minus a little m over uppercase M to the 1/4, I guess. I don't remember which one of those two I was looking at. But in either case, you know, I looked at this, and in the paper it says, oh, and the answer is, and I thought, I kind of wanted to give this to you all, but it wasn't so clear to me that this was gonna work. Okay, because I mean, you know, when I first looked at it, I thought that it was going to take a different integration technique. But actually, and the authors never mention whether they kind of came up with the numbers, the exponents they did, because then it works out nicely, or if they just modeled things, came up with the particular exponents of the 3/4, and then it worked out. And that's always great, you know, because you kind of think like, oh, you know, there's something to this nature thing, and everything working together, and the mathematics works out, and all that. But we want to concentrate on this one, on that form. And so I'm going to just get rid of this other. So the trick here with separating the variables, one is, well, that is everything involving M. And I would leave the A on the right-hand side. You could take the A with you because it's just a constant multiplying everything. But because of that, it's usually when you do separation of variables, any constants that you can leave on the right-hand side is just easier. And so, when you divide everything by this, right, you get dm dt all divided by m to the 3/4 and 1 minus m over uppercase M to the 1/4, and then equals A. And so when you go to integrate this thing on both sides by t, you know, this will be easy. You get at plus a constant, right? You know, so that's not a problem. So the key here is, and this is where it just works out wonderfully, is if you let u equal that thing, your derivative ends up basically being that thing. Up to constants, right? You always have constants to worry about, but right? So if you let u equal 1 minus m over uppercase M to the 1/4, then when you take that derivative, well, the 1 goes away. That's very important because otherwise this just wouldn't work out. So I get a minus 1/4, and I get this m over uppercase M to the minus 3/4. And then the derivative of what's inside, I guess I get a 1 over m, like that. And then a dt. Okay, so you need to, that m is just a constant in this negative 3/4, and there's an m to the negative 1, and you need to pull all that together, because what you're interested in is the fact that I've got a little m to the negative 3/4, because that's exactly what you're dealing with there. Okay, so that's your m to the negative 3/4, and then after I do the dt part, then times dm. And so, I've got that and that taken, that should be an m. These two parts taken care of, and the rest of it, there's a negative, a 1/4, and I guess, so here, right, this is 1 over m to the negative 3/4, so that's m to the 3/4. And so the two of those together make an m to the negative 1/4. But again, that's just a constant, that uppercase m. And so, I'm going to need that, right? So in all of this, eventually I'm going to have this m to the negative 3/4 dm over here, and that's my 1 over u there. Right, but I need a negative 1/4. Oh, okay. So I need a negative 1/4. And this, like I said, I think this becomes an m to the negative 1/4, uppercase m. And so maybe you put in there negative 1/4 and m to the 1/4. Okay, you need that. And it's not there. Oh, I can't, oh, wait, that was negative 1/4. I need that constant, but it's not there. We'll just put it there and then divide by it on the outside. And I turn this thing into, I'll just have a du over u with a funky constant out in front. Okay, so that's the idea. Okay, that's how you want to get at that with the separation of variables. So it's still kind of messy, but now some of the things you can do when you start getting messy constants. Oh, I don't know. Just I wouldn't go with c for a constant, because usually you end up with your plus c, so that would bad idea. How about a k? Right? Is that you need a constant here, k m to the negative 3/4 dm, and you have that 1 over k here, and equals at dt. oh, wait, that K disappears because that went with the dm. So you get this 1 over K times that. And so if you want, and I don't remember how the solution is written, it says, hey, show that this is true. And like I said, I don't remember exactly how that's written. But as I look at this right now, I'd probably say here, if you could, just multiply both sides by K and put the K with the A, right? AKT there, because then that's just a constant. It's AK. And notice I said AK because the alphabetical order, I guess. But I probably wouldn't try, if I didn't have to, like I say, I don't remember what it says to show, and I was just trying to get you to go through their paper in essence. So it may be that whatever you need to show, it might be better to leave the 1 over K over here. But again, it's just a constant. And so, yeah, I got messed up in there, didn't I? K, and I had the 1 minus m to the 1/4. I guess I was combining two things at once. I hadn't made my substitution yet because I still had m. So I do want the K, right? That's going to be my du. This is going to be 1 over u, and so I get that. And so if I can set it up and just think about it that way, and then whatever that is, then put that back in when I'm ready, right? But it just makes my life easier if I don't have to write so much stuff. And so I would have this 1 over K, now making the substitution, du over u, and, See, you people need to start yelling at me for doing crazy crap, okay? There's no T after that, right? There was just an A over there. Sometimes I'll write something down, but actually do the integration as I do it. So this might be an apt time to mention, on the first two videos that I put up so far on Chapter 7, the exercises, I think it was the first one, I had like 8/3, and I wrote it as, then next I wrote it as 8/8, and I went, oh, that's 1. Okay, I was wrong. I mean, that was a simple transposition error. So I went back and figured that out when I got two different answers for the same thing, but left it. Because again, I think it's important to realize that, I do pretty well with math. And that's what I say in the video. I've gotten a PhD, I've published papers, I've worked in industry, and all that, and I still do stuff like this where I write down the A dt, but in my head I went, well, that's going to integrate to AT, and so I write down AT. I still do stuff like that. Could be my ADD, I don't know. But the idea that you'll never make a mistake or something like that, no, that's just not true. You're always going, if you keep doing math, probably anything you keep doing, you will always make mistakes. Okay, the question is, how do you catch them? Right? And that's a big part of doing mathematics, is realizing that, okay, yeah, I wrote something down wrong, But then I looked at it again, and I went, oh, wait, that's not what's going on, and, you know, and I catch it and I fix it. I don't always, but, you know, it's very easy when you're writing all these symbols down to write extra stuff. And then, of course, standing up here and talking to you while I do it, it's really easy to get off on what's going on. You know, but there are things you can do, like, oh, that's kind of complicated. Don't leave it as complicated. Just make it something else. Make it something simple. Work with that and then put it back when you're ready. Okay, so we would have something like this, and then our AT plus C. And see, this is where, notice that, see, if I had multiplied through by the K, at that point, you know, before I did the integration, I would have AKT plus C. But when I do it now, if I multiply it through, I would have the natural log of the absolute value of u equals AKT plus KC. But actually, that's no different than if I just had the C, because we don't know what that C is yet anyway. Okay, and those to me are the important concepts to kind of keep with you in all this symbol pushing stuff, is that that is a arbitrary constant, arbitrary. So at this point, it doesn't matter what it is, but it needs to be there. And so, if I multiply it by something, who cares? I can, now what I was taught to do, or the way I was taught, I don't know that you would say I was taught to do it this way, but my teachers would then rewrite something like this as AKT, and they would write C again. Okay, now that's sort of voodoo. But if you know the context, you realize, oh yeah, sure, it's still just that arbitrary constant I don't know, but probably better form would be to put some subscripts on them so that you realize that C and that one are different in the sense that of how I got to them and so forth. But again, I don't know what it is, so who cares? What it is. You know, I can name it C1 or C6 or whatever. Okay, so that's that separation of variables, and then I would exponentiate both sides. And the big thing there when you do the exponential, right, is that you get, you know, e to something, and again, I don't remember what form it's in, so maybe it's in the form without the K, you know, without this other stuff there. I just, like I say, I don't remember. But when you have that, that plus means I could instead write that as e to the c. So multiplying e to the c just by powers, you know, the properties of the powers, and then I can name that something new. And that is what happens, is that gets named M0. Okay, so instead of C1 or C2 or something, it gets named something very different, M0. So that's probably all I'll do at this point with that. So if you were still having trouble with that, it is, you know, this is a, it's kind of weird but wonderful the way that worked out with the 1/4 there and the 3/4 there. I didn't see that coming when I was first reading through this stuff, and like I say, they make that 3/4 out to be a modeling result that if you look at data, they say, oh, that's the way the mass works. But it also turns out to be extremely convenient for getting a nice analytical solution to this model. So it does work out that way sometimes, though. So, I'm not sure if I ever mentioned, I think I probably mentioned to you once when we started talking about derivatives, is that, yeah, I had a guy at University of Kentucky in food science, I think it was food science, was working with diets and rats and that sort of thing, weanling rats. And he had, some sort of similar kind of thing. He had a model, but he wasn't solving it. He was using numerical stuff, and so it gave him no insight as to what the answer meant. And I happened to talk to him because my wife was in food science and so forth. And it turned out I could take the derivative and set it equal to 0 and solve for the maximum. And he was overjoyed. Okay, so just being able to do some of that symbol manipulation can help you out greatly in understanding what a model does for you. More than just, oh, it looks like the data. It can give you insight as to what's going on. Okay, anything else at this point? Any other questions? No. Okay. Let me go back here just real quick, because the other day, okay, everybody's still there, so the sound must still be working. Great. It's always good. Yeah, the other day the sound quit working. Worked fine on the recording, but it didn't seem to go through Google Meet. Okay, so on to chapter 7. And actually they, between the book and me, we've given you some indication of 7.1, because the text actually, it was introducing this, and this is where your exam problems came from, was that the text already introduced the idea of kind of finding these general areas. And so let me introduce 7.1 with the exam, where it said it wanted a region bounded above by y equal x squared and 2 minus x, and then and below by the x-axis. Okay, so when you draw that, there's x squared, and then 2 minus x is going to come in here like this. And so there's your region bounded above by the two of those, and below by the x-axis. And the thing is that, that where that was just beyond what I think what they did in the text. Now I have to think about it a minute. They might have done a problem like this somewhere in there, like in the homework or something like that. But the idea was to take this just a bit beyond what the text had done. And the way it's just a bit beyond is, we were just told, well, just, take the height of the function, any positive functions, and do that integral, right? So that's 0, that's 1, that's 2. But the thing you had to worry about was the function changed. So in order to do this, the way we did it in chapter 5, we did this. In order to do this, or maybe even chapter 4, gosh, I can't remember. It's in the book somewhere. The way we, did this was we thought of making rectangles every time that started here at the x-axis and went up. I should set the record straight on something, though. So everyone, including me, actually got a problem wrong on the exam because I didn't write it quite correctly. I gave you all credit because from what we'd done in class, it just kind of flowed. And that was the problem about left-hand sums in a decreasing function. I said, argue that that's always an overestimate. Well, actually, that's not true. It's an overestimate if the function is positive. It's an underestimate if the function is negative. So I needed to add in that statement that the function was positive. And I either forgot at the time or I just didn't think about it. And I was thinking about it as a positive function when I wrote it. But anyway, so that did need to be said, I think, is that actually we were all wrong on that. Most people did a very nice job on arguing about that and drawing a nice picture and so forth. But yeah, we were all wrong because we could have drawn a negative function, negative valued function. Okay, so again, so like I say, I'm wrong all the time. Okay, but I usually catch it. And now, so we want to find this, and the way you would have done this on the exam would have been you done an integral from 0 to 1 of x squared dx, and then you'd have added to that the integral from 1 to 2 of 2 minus x dx. And neither of those is too difficult to evaluate, but nonetheless, that's what you would have most likely done. What chapter 7 really introduces is that easier is a funny word here, but there may be an easier way. Okay, and that goes into the idea of, well, I can use whatever rectangles I want to use, or think of it like that, as whatever rectangles I want to use. And so, if I used rectangles that go this direction, then my functions never change. Right? This function is always on top, and that function's always on the bottom. So, in a way, that's easier. Now, where it's harder is we're not used to that. Okay? We don't look at graphs that way. We have had years of indoctrination of thinking about everything sort of going up from the x-axis or down from the x-axis. Everything's in a sort of a vertical fashion. So to call this easier, I'm not so sure. However, it turns out that it becomes important as you generalize to more dimensions. So as that happens, and you want to do integrals, there are some integrals that you could only do by thinking of them as one of these two directions, either the vertical or the horizontal. But the way now I drew rectangles, and that's the way you all have been introduced to it and so forth. But actually, when I do it myself, and what I like to introduce to you is to start to think of it, instead of as rectangles, think of it as slices. Now, it's a pretty subtle difference, because what's a slice of this? Oh, it's a really skinny rectangle, right? I mean, because, okay, here's my wedge of cheese or something that at the store, and I have them slice it up, but what I kind of think of is not really the rectangle itself that's formed from the slicing. I think of the slice not as the piece of cheese that I get out of it, but the slice is the action of making the piece of cheese. Very subtle difference. But in that way, I tend to just kind of think of lines going through here like this, that then I could make into rectangles. Okay, but I think what you're really doing in the limit is you're adding up these slices, not those slices, but the places you sliced. And you just end up taking an infinite number of those slicings in order to do this. It's, like I say, it is a subtle difference, but I think it's an important difference. And if you can start kind of thinking of doing these integrals for area and so forth as to how you slice it as opposed to rectangles themselves. So here, I'm slicing it vertically. Here, I'm slicing it horizontally. Okay? And when you do that, then, what your integral does is your integral goes from the first slice to the last slice. So in this case, here's 0, here's 1. Our integral in this case would go from 0 to 1, as opposed to here, well, it goes from 0 to 2 overall, but I have to break it up into two pieces. Okay, so it's this idea of slicing that way, and when I slice, I'm kind of thinking of what axis did I slice up? I sliced up the y-axis here. So I need y to go from 0 to 1. And then any given slice, what does it do? Okay, back here, a given slice went from 0 up to x squared. Okay, so I got my height as x squared minus 0. X squared minus 0, x squared minus 0, and so forth. That's how I got the height of a slice. How did I get the height of the slice here? Oh, that height, 2 minus x, minus 0. That's how I got the height of that slice. And I'm just adding up all those slices. Here, same idea, but now how do I get the height of that slice? That's where the textbook starts talking about y. And so this is, here we've got y equals x squared. okay, if y equals x squared, then that means x equals the square root of y. Now, here you got to be careful, right? Because, well, I could have used minus as well, but I'm over here with plus, right? X is positive, y is positive. Okay, x is positive, y is positive. And then, here, this one is 2 minus x, or y equals 2 minus x. Well, that means that x equals 2 minus y. Just bring the x over there, take the y that way, or whatever you're going to do. To me, that's kind of the way I think of it, adding x to both sides and subtracting y from both sides, and I get x equals 2 minus y. And so that height for any given slice goes from 2 minus y down to the square root of y. And then that's dy. Now, if we are correct about kind of how we're thinking about these problems and how we're modeling them, we should get the same darn answer. Right? Because we're modeling the area of this. Here, I did it with the vertical slices. There, I did it with the horizontal slices. So I should get the same answer. Okay, so the x's, so I have the integral from 0 to 1 of x squared dx plus the integral from 1 to 2 of 2 minus x dx. That is x cubed over 3 from 0 to 1 plus 2x minus x squared over 2 from 1 to 2. And so this is 1/3 plus 4 minus, that'll be a 4 over 2, that'll be 2. Minus, and then putting a 1 in, I get a 2 minus 1/2. And so this looks like, what? That's 2. And minus 2, oh, that's 0. And then a minus and a minus. So I get 1/3 plus 1/2, which is 5/6. And that sounds familiar. I think that's what it was. Now this other one, we have our integral from 0 to 1. And we have 2 minus y minus the square root of y, or y to the 1/2 dy. So this is equal to 2y minus y squared over 2 minus, now this is y to the 1/2, so that'd be y to the 3/2 over 3/2, or times 2/3. And this is from 0 to 1. So we get 2 minus 1/2, and then minus 2/3 minus, really? Well, we'll have to think about that for a second. 2 minus y and y squared. Did I get my negatives? I didn't get my negatives mixed up, did I? Oh wait, there's a positive 2. Yeah. See, I was looking at this as the 1/2 and the 1/3, but it's 2/3. So we're probably fine. Okay, so this is 3/6, 4/6, so 7/6. Oh, beautiful. Okay, 5/6. So there was a case where I thought I was wrong, but I was mistaken. So, okay. So we get 5/6 either way. As we should, because we're modeling the area shouldn't change. Now, I think the more important aspects of this, so you can get all wrapped around the axle about these various things, so here we found the difference between the two curves and so forth. But the mathematics, what you need to remember is the integral doesn't care what you're doing. The integral is just a calculation. And you get to interpret it any way you want. So here, I'm interpreting this integral as horizontal lines that I'm adding up, all their lengths. Okay, so I'm adding up all those lengths, well, times that infinitesimal width. So I'm adding all that up, and I'm thinking of those as horizontal between two curves. But what's to stop me from saying, oh no, that's not what that is? What that means is I have y there. Why not? Right? We've named variables things other than x. We've used theta. We've done this and that. Right? We can name it whatever we want. And so there's y. And I happen to have this function. 2 minus y minus the square root of y. Okay? Now, what the heck does that look like? I don't know. It starts at 2. And by the time I get to 1, it's 0. What's it do in between? Well, it's 2 minus y, so, it's kind of like that. But then I'm also subtracting off the square root of y. And so it probably, I could take derivatives to determine the concavity and so forth, but I'm pretty sure that's my function. That function. Right? It looks like that. And so I can interpret this as slicing it up that way and getting my area from that. So it says this area is the same as that area. Okay? But those are, I think, different shapes. Pretty sure they are. Because that's a right angle. That's not. Right? So you could say, oh, well, really, they're the same shape and they're just bent different. Right? No, they're not the same shape at all, but they have the same area. Okay? And how do I know they have the same area? Well, because that integral found the area of this and found the area of that. Same integral, same area. Okay? And that goes back to integrals are not areas. They are an interpretation. To think of area, I can model an area using an integral, and it is a great way to build your intuition with graphics and all that. But an integral is not an area. Okay? Because that one is the same as that one, and we could use the same integral. Well, as long as I slice that one that way. And I can use the same integral. And they are not even the same shape. Okay? Now, the textbook does something I think is just horrible. They talk about an f of y and a g of y and that kind of thing. The text, and I did give you one problem on this, textbook problems, and it's both, you know, in the sense of doing math problems, but it's also, I think, problematic the way they do this. They mention, like, I'm going to use a g of y, and when they do that, the way they think of plotting this is still, there's y, there's g of y. So they give you, now we call these a right-handed coordinate system when x is here and y is there. Now the reason we call it right-handed is if you add a third dimension and you do it the correct way, you put your right hand on the x-axis, curl your fingers toward the y-axis, your thumb will point in the direction of the z-axis. Okay, that's why it's called a right-handed system. Well, here, all of a sudden, see this, I mean, we're calling it y, but if this is the function, then this is the opposite direction of that. This is a left-handed coordinate system. And, well, in order to get z coming out this way. So it would be a left-handed coordinate system. But it's definitely backward from the way you ever look at x's and y's, you know, or independent and dependent variables. And so when they mention this, and this is in particular, I think I gave you one exercise, and I think it's exercise 25. Okay, this is how the book kind of introduces it in the text. You know, they'll talk about a g of y and so forth. Okay, now, and I do have a video up on exercise 26, and what I tell you is, don't pay attention to them. Don't do it. Okay, you're given g of y. Fine. Make that the y-axis. Make that g of y. You just renamed whatever your independent variable was. Do it that way. Now, they're doing it for sort of a drill, but I guess to me, what's even more important is for you to realize you are in charge. Okay? The mathematics is simply some algebra symbols. How you decide it translates from the algebra to the graphical is up to you. And it's way easier to translate it this way. You know, we are just not used to looking at things this other direction, where that's the independent variable and that's the dependent variable. Economics, oh, it can get crazy. Okay, you take a microeconomics course, and because of historical things, some of their models put the independent variable on the y-axis. It's horrible. After you get used to it, it's not so bad. But the intuition doesn't work the same because we are almost, at this point, after enough years in school, we're almost just hardwired to look at the independent variable there and the dependent variable there. And it gets really hard not to do that. So if you can, sure. Just, you know, okay, they tell you g of y, it doesn't matter, it's y. There's the y-axis. There's the g of y-axis, okay? All right, well, so we're out of time. I will continue to try to add some videos, get some more stuff up there for this module, and I will see you all on Thursday.